Hi everyone, today we're doing math induction, new topic, okay? Let's look at example 1. Okay, so we are doing something called the induction step, which is the first step in a proof. And all you're doing today is just practicing this induction step. So you're gonna give evidence that this statement is true. Okay, so the statement says show that the sum of all odd numbers always equals a square number. Okay, so we're going to take the first odd number, which is 1, and we're going to show that that's always a square number. Well, 1 is a square number, so 1 is equal to 1. And now we try that for n equals 2. So for n equals 2, you take 1 plus 3, and you show that that's a square number. So that's equal to 4. So 4 is a square number. And then we do that for n equals 3. So this is for n equals 3. You're going to plug in 3 odd numbers. So 1 plus 3 plus 5. So that's how far your sequence should go. It should go out to 3 numbers. So that's equal to 9. 9 is a square number. So it seems that this is always true. The sum of all odd numbers always equals a square number. So we're going to try that for n equals 4. That means we're going to go out to 4 numbers in the sequence. And that's equal to 12 plus 4, that's 16. 16 is a square number. And then finally one more. We just add another odd number. So we're looking at the odd numbers. So we just add one more odd number. That equals 25, and 25 is a square number. So you see a pattern, and then you generalize. You make a claim. Our claim is that the sum of all odd numbers is always going to be a square number. And the way that we're going to write that is if you take the sum of all the odd numbers all the way up to, we're going to call that the last odd number, that's always going to equal a number squared. Okay, so this is our claim. Our claim is kind of like a formula. And in the next lesson, we'll be doing proofs. So we'll get to the next step, which will be to actually prove this. But for today, you're just doing the induction step. So in the induction step, all you're doing is showing evidence that this seems to be true. Okay, and that's it. That's all you're doing. Let's look at example 2. Okay, let's look at example 2. Now this one says, show that the sum of all even numbers always equals n times n plus 1. So here are my even numbers. Show that that's always equal to n times n plus 1. So again, we start with s sub 1. That means you take the first even number and you show that it's equal to n times n plus 1. So I'm going to plug in n equals 1. So if I plug in n equals 1, that's going to be 1. And 1 plus 1, that's 2. Okay, so do I have the same thing on both sides? Yes. So it's true for the first even number. Now what if I take s sub 2, which means I take 2 even numbers? Because I'm looking at the sum of all even numbers. So does that equal the other side if I plug in n equals 2? Well, if I plug in n equals 2, that's going to be 2, and 2 plus 1 times 3. So again, I get the same thing on both sides. I get 6 equals 6. So what you're showing is that the sum of all the even numbers will always come out to equal this. So let's do one more. If n equals 3, that means you take the first 3 even numbers. does that equal the other side if I plug in n equals 3? 3 plus 1, that's times 4. So this equals 12 on the left side, and it equals 12 on the right side. So then they're the same on both sides. Okay, then you would continue to do that. And if you have enough evidence, you would say, well, it worked for the first 5 numbers, so it seems to be true. The sum of all even numbers will always equal a number times the next number, n times n plus 1. So what we're doing is we're gathering evidence, not to make a conclusion, but just to pose a question. So if we have enough evidence, can we pose a question? Can we say that this is true for any number n? Okay, so that's what I want to end up with, a conclusion. So assuming that you did S of 4 and S of 5 and it seems to work, then you would jump to the claim. We're going to say if you take the sum of all even numbers, and I'm going to call the last even number 2n just to get a little fancier. Okay, so if I take all of the even numbers up to any number, that will that always equal n times n plus 1? Okay, so here's the formula that I'm trying to prove. Okay, so again, this is called the induction step. You're just going to show that this is true for a couple of cases. All right, now let's look at example 3. Okay, in example 3 it says, show that the sum of all square numbers always equals n times n plus 1 times 2n plus 1 divided by 6. Now it's getting a little more complicated, but this will always equal the sum of the square numbers. So again, you try the first one, and let's see if it's true for the first one. I take the first square number, and I show that it's equal to this side if I plug in n equals 1. So on this side, I'm going to plug in n equals 1, and 1 plus 1, and 2n plus 1, that equals 3, divided by 6. Okay, so this turns out to be 6 divided by 6, which does equal 1, which equals this side. Okay, now let's try if n equals 2. That means you take the first 2 square numbers, n equals 2. So 1 squared plus 2 squared. Does that equal the other side if I plug in n equals 2? Well, if I plug it in on this side, it's going to be 2, 2 plus 1, and 2n plus 1, that's going to be 4 plus 1, 5, all over 6. And that equals 5, because that's 6 divided by 6. So again, 5 equals the sum of the first 2 square numbers. So you're just checking that this side is equal to this side for any number. Okay, we'll do one more. If we take n equals 3, can't see that. Okay, so for n equals 3, I would take the first 3 square numbers. So that's 1 squared plus 2 squared plus 3 squared. Does that equal the other side if I plug in n equals 3? 3 plus 1, 2 times 3, that's 6 plus 1, divided by 6. Okay, so what does that equal? 12 divided by 6 is 2 times 7, that's equal to 14. If I check this side, the sum of the squares equals 14. So it's the same on both sides. Okay, then you would continue. Do S of 4 and S of 5, and if it works for all of them, then you can start to say, hey, I think that we're onto something. I think this is going to be true for any number. So then we write the formula. We would say the sum of all square numbers is always going to equal, and here we could say all the way up to n squared. So the sum of all square numbers to any number will always equal n times n plus 1 times 2n plus 1 divided by 6. So we have a formula. Okay, we have a claim. All right. So this is called the induction step. The induction step is just showing evidence that this seems to be true. Okay. All right. Now let's look at, you have a box problem today. Well, actually, you have a U-try. But after you do the U-try, I'm going to get you started on the box problem. Okay. So in the box problem, we have something called Fermat's formula. And this says that 2 to the power of 2 to the n plus 1 always ends up being a prime number. Okay, so let's plug in the first one. If I plug in n equals 1, okay, so 2 to the first power is 2, so 2 to the second power is 4. So 4 plus 1 equals 5. 5 is a prime number. So the first one is true. Now let's plug in n equals 2. I know this is kind of weird. It's 2 to the power of 2 to the power of 2 plus 1. Okay, so 2 to the second power, that's 4. So 2 to the fourth power plus 1, that's 16 plus 1. This one's also a prime number. Okay, so I have evidence that this is true. Let's try another one. 2 to the power of 2 to the n power, which n is 3. Okay, so 2 to the third power is 8. So that's 8. So what I have here is 2 to the 8 plus 1. So that's, what is 2 to the 8th? Let's see, our calculator. I have 256 plus 1 is 257. So this also ends up being a prime number. And the way that you know if it's a prime number is if it could only be divided by itself. So for example, 5 can only be divided by 5 and 1. There's nothing else that divides 5. 17 can only be divided by itself and by 1. So if it could only be divided by itself, then it's prime. Can only be divided by itself and 1. That makes it a prime number. So what I'm saying is that nothing goes into 257. The only thing that can divide 257 is 257 and 1. Okay? So once these numbers get bigger, it's going to be kind of hard to decide if it's prime. So I'm going to have you use a prime calculator. So I'm going to have you go online, go to math.com, and then click on the prime calculator, plug in the number, and it'll tell you if it's prime, if it could be divided by anything. All right, so I'm going to have you finish this, and then